Okay, so 11.4 starts out, we're talking about limits at infinity and limits of sequences. So hopefully we had it correct in the schedule that you were doing 2627, relatively close to this chapter. That's usually what we try to set up. So if I was going to do this problem, I would first start with the x plus 1, and I would set that equal to 0, and if I subtract 1, I get x is negative 1. So I'm going to go to my graph and go negative 1 as a vertical asymptote. And then what we learned is that I have a first degree polynomial on top, x to the first power, and also an x to the first on the bottom. So that's first over first. So what that tells me to do is take the leading coefficient, 2, and the leading coefficient on the bottom, which is that 1 right there. And I get 2. So I'm going to go to 2 and put a horizontal asymptote. And then I know my graph would be here and in here. Now, I know there's some sort of intercept there, but I'm not worried about the intercept. So one of the things we can talk about is what is happening as x goes to infinity. Well, infinity is out here. So you can see my graph in this area. I should switch colors. Over here in this area is getting very close to the horizontal asymptote, and so that's going to be a 2. And then when I go limit as x approaches negative infinity, that's this way over here, you can see in this area again that it's getting very close to 2. So basically what we talk about is infinite limits are the horizontal asymptotes, and we can have multiple horizontal asymptotes. So you could have a couple different ones, and going to infinity or negative infinity would give you different answers. So let's take a look at what's happening. So if the degree of the denominator is bigger than the degree of the numerator, what I call small over big, then we have horizontal asymptotes at 0, which means the limit would go to 0. If the degrees of the denominator and numerator are equal, then you do the leading coefficient rule, I call it. So y would be what I call LC divided by LC, the leading coefficient divided by the leading coefficient. And then finally, if the degree of the numerator is bigger than the degree of the denominator, there's no. So back in 2627, we called it a slant asymptote. The graph could go up, slant upward or downward. So there really is no limit. And I'll talk to you about this when we get there. I'll show you an example, and we can show some understanding. It's just what it approaches. So let's take a look at a couple. Okay, so my example's got a little squished together, but that's a first degree. So I have a first degree over a second degree, and I would call that small over big. When that happens, my limit will be 0. And you can graph this and notice what's happening. Make sure you put parentheses around the top and the bottom, but it goes to 0. The next one, they have the same power. So you have equal degree. Well, then I'm going to take the negative 1, which is the leading coefficient, over the 5. And there's my answer. So what I'd like you to do is try C and D, and then come back and check the answers. All right, so hopefully you paused and you wrote in C and D. So with C and D, I would say, oh, this is big over small, because I have a power of 3 on top and a power of 2 on the bottom. Now if I graph this on my calculator, so if I go over to the calculator and I type this in, I have to do a parentheses, negative 2x raised to the third plus 3x squared plus 1, so what I would say is as x goes to infinity, so way out to the right, notice it's slanting downward, going to negative infinity. Or if I go to negative infinity, the graph is slanting upward. So sometimes you can show a little bit more understanding by describing what the slant is doing. So you can tell someone which way it's slanting. But for now, you can also say because that's happening, there is no limit. And then this one, notice the order is kind of switched. So if it helps, you might want to write negative x plus 1. So this is both first over first. And this is the term I want you to concentrate on. So now it's 2 over negative 1 because you do the leading coefficient, and you get negative 2. So when they do this stuff on the bottom, those of you in my class that do the online web work problems, a lot of times web work will try to trick you by not putting everything in descending order, and you got to make sure you find the largest exponent. This one, the n right there, the n plus 1 quantity squared, I'm really supposed to FOIL or box method that, but I'm just going to tell you that it's n squared and some other stuff times another n squared times the 6. So what we're really looking at is we have a 6n to the 4th. And I'm going to put some dots there. I know there are more terms, but I don't need them. And then on the bottom, I have 4n to the 4th. Well, they're equal degree. So I do 6 over 4, which is 3 over 2. All right, I'm going to pause now and have you look at F and then do letter G maybe also. But look at those two answers. See if you can figure them out and then come back and see what I say about them. Okay, so part F, there are really two things going on. And so this one, what I would say is this is a 0 degree over second degree. And so that's going to go to 0. Again, this is infinite limit. So that term goes to 0. Nothing happens with the 4. So what I end up with is 4 minus 0 for a limit of 4. So there are two parts to this. This is a constant of 4, and this one will go to 0. So go ahead, and if you want to try to pause it here and try this one, do it. Otherwise, we'll take a look at the answer. So something here is happening the same way. As I go to infinity, I get 6. Now on this one, I would say this is a second over a second. So that's 5x squared over technically x squared plus 6x plus 9. But I only need to worry about the 5 and the 1 in front. So 5 over 1 is 5. So now I bring it over here, and this is going to be 6 minus 5, and I get 1. I get 1 from my limit. Okay, so just to take a moment here, after teaching 11.4, then students come in and take the test. I've had students in the past that have done the infinite limit rules for every limit on the test. Now remember, some of our limits are what's the limit as x goes to 0 or x goes to -2. You can't use the infinite limit rules if you're not approaching infinity, so just be aware of that. Sequences, one of the things that we can do with sequences is plug numbers in until we know what's going on. So like if I plug in a 1 here and here, I end up with 3 on top and 5 on the bottom. And if I plug in a 2, I get 5 and 6. And plug in the 3, I get 7 over 7, which is 1. And it keeps on going. So there's my 1. Then the next number will be 9 over 8, which is 1.125. 11 over 9, which is 1.222. And 13 over 10, which is 1.3. And so what we talk about is these numbers are getting bigger, but the gap between them is getting smaller. So 1 to 1.125 is a difference of about 0.12, so 0.125 to be exact. 0.125 to 0.22 is about a tenth, or 0.1, and 0.22 to 1.3 is 0.78. So what you're seeing is the gaps between the numbers are getting smaller. And if you kept doing this, eventually it levels off. Well, when you think about it, where do sequences stop? Like, how many numbers can I put in for n? Well, it's still going to be our infinite limit rule. So I still have a first over a first, and so there are my leading coefficients, 2 and 1, or 2. Pretty easy. If you're working with the sequence, you still use your infinite limit rule. Down here, second over second again. So I do 2 over 4, which is 1/2. Okay, so the example 3, they're trying to be a little bit tricky. So if you put in a 1, so start with n is 1, I get -1 to the second power will be a 1. And on the bottom, I get 1 squared, which is 1, so I'm getting 1. Then when I put in a 2, I get -1 cubed over 2 cubed. So that turns out to be -1/4. And then put in a 3. So again, now you're at -1 to the 4th over 3 squared, and I'm at 1/9. So what's happening is your number is up here, then it's down here, then it's up here, then it's down here. And slowly these numbers are getting closer and closer to 0. They're oscillating up and down. So the point is, the numbers on top are always 1 or -1, 1 or -1. So the number on top is really a 0-degree polynomial. The bottom is a second-degree polynomial. It's going to go to 0. Okay, so this one, you could type in this data if you would like and graph it, the scatter plot. You can't really see what's going on. You got to zoom in on your window, but you can use this equation also to put in 13 and 14. So if you want, you can put those in for the time. Now notice t is between 6 and 12, so you'd be putting in 13 and 14, not 2013, not 2014. What I'm more concerned about is what's happening as t goes to infinity. And it's a little bit tough to see, but we're going to do, you look at it, this is a first degree and a second degree. first degree and a second degree. So because we're going to infinity and it's a first over a second, this thing is going to go to 0. So the next question down there, is this a good thing? Well, no, this would not be good, because if you're in charge of the ready reserves, eventually over time, you're not going to have enough people to do the work you need to do, because you're going to have 0 people working or participating in ready reserves. So it's the same thing as looking at population of white-tailed deer. From year to year, they may go up or down a little bit, but we would study long-term behavior. We study the effects as t or time approaches infinity. So 20, 30, 40 years from now, I would not want whitetail population going to 0 either. That means they're going to extinction. I also don't want them to be a slant asymptote going right off the charts, growing without bounds. So that's 11.4.